Hi everyone, welcome back. In this lesson we're going to be talking about indefinite integrals and the net change theorem. And first I want to mention that we've been discussing this whole topic, this whole idea of definite integrals. And that's where we identified that these definite integrals were finding some area underneath the curve, and it was more of a net area that was being identified. And that was that if we had some function, we could integrate that function from a to b. Again, those were the limit bounds for the x values for the function f of x with respect to the variable dx. Now, we're going to be focusing more in general in this particular instance that we want to find an indefinite integral. And when you see on what you see on your screen towards the top, we have on the left-hand side a definite integral. And on the right side, we have an indefinite integral. And the difference between them is that the definite integral has bounds. It has the bounds from a to b. An indefinite integral does not, meaning we just want to find, in general, what is the antiderivative for the function. In other words, what is the integral for the function? In general, no bounds. In that particular instance, we need to account for the constant c. And again, c could be any given constant that we have. So, indefinite versus definite, we must always identify what type of integral we are working with, and once we identify it, we then need to keep working. Is it in general or does it have bounds? And we need to evaluate that. So you're going to see here on these examples that I've written down, it says evaluate the integral. For part A, we have the integral for the fourth root of x to the fifth dx. And the way we want to evaluate this is we want to interpret the integrand in terms of its exponential power. So in order to do that, I'm going to write the integral for x to the power of 5/4 dx. Now this, first and foremost, is an indefinite integral. Which means when I find this antiderivative, I need to find the antiderivative in general, and I need to assign the constant to it. So if I take 1 and I add the exponent there, so 1 plus 4/5, that's going to get me 5/4 plus 1 gets me 9/4. And I multiply by the reciprocal, which is 4/9. There we are. So everything's looking good so far. Then we just attach a constant plus c, and we're done. That is the answer to this particular question. There's nothing more that we can do because we're not given bounds, so we cannot evaluate. Therefore, this is our general answer. Part B, we're asked to evaluate the integral for the function of u squared plus 1 over u squared with respect to du. Again, the first thing I want to do is rewrite this so that I know how to evaluate this. I want to make sure I get the powers that I can evaluate on the exponent, on the variables. So I have the integral for u squared plus 1 over u squared can be rewritten as u to the power of -2. And this is all du. Now I just do a term-by-term integration. Integral of u squared, well, I add 1 to the exponent, multiply by the reciprocal. 1 with respect to du, that's going to be u. Add 1 to the exponent for u to the power of -2. That's going to get us u to the power of -1, multiply by the reciprocal, and that's going to be -1. And I need a general constant term. So I need a plus c. Let's simplify this a little more. Typically, we don't like to leave negative exponents. And here's our final answer. There we are. So one of the things that we identified here is that once again we were working with an indefinite integral. So for part C, I want to work with the integral from 1 to 2 for the function of 1 over x squared minus 4 over x cubed dx. So again, I'm going to identify really quickly. I have a definite integral at this time. And because I have this definite integral, I'm going to say that I need to evaluate the antiderivative at the given bounds. So first, I need to find the antiderivative, but the function is not in the form that I would prefer to find an antiderivative for, which will now rewrite as x to the power of negative 2 minus 4 times x to the power of negative 3 with respect to dx. Find the antiderivative here. Antiderivative for x to the power of negative 2, we add 1 to the exponent, multiply by the reciprocal. Add 1 to the exponent, negative 3 plus 1 gets us negative 2. Multiply by the reciprocal, so that's going to be negative 4 is going to be multiplied by negative 1/2. Negative 4 times negative 1/2 should give us positive 2. Evaluate this from 1 to 2. All right, let's keep going. We're going to evaluate the first function. Or you know what, let's go ahead and interpret the negative exponents really quick before we evaluate. This is going to be negative 1 over x plus 2 over x squared. We evaluate this from 1 to 2. So let's go through that evaluation process. I'm going to substitute in the value of 2. As such, minus the function evaluated at 1 plus 2 over 1 squared. All right, the first term is going to be negative 1/2. Second term is going to be 1/2. Next term, negative times the negative, that's positive. 1 divided by 1, that's 1. Again, distribute the negative, and that's going to be a plus 2. Oh, sorry, my apologies, not plus 2, minus 2, because we distribute the negative. 1/2 and negative 1/2, they're going to cancel each other out, so they go away. And we're just left with 1 minus 2, which gives us negative 1. That's the final answer. And so again, we must always go through the process of trying to identify what is the integral that we're given. Is it an indefinite integral or is it a definite integral? And then we go through the evaluation techniques that we've learned so far. Let's go with part D. So part D, we're going to do the integral of secant of t multiplied by secant of t plus tangent of t dt. And again, we're going to identify that this is an indefinite integral. Because it's an indefinite integral, we're going to need a constant, and we're not going to evaluate at the given endpoints. And so again, this integrand is not in any form that I've seen so far that we can evaluate, at least for this class. So what we're going to do is we're going to distribute really quickly the integral for secant squared of t plus secant of t times tangent of t dt. The integral for secant squared, well, the derivative of tangent gets a secant squared, which means the antiderivative for secant squared is tangent. So we have tangent of t. The derivative for secant of t is secant times tangent, which means the antiderivative, or the integral for secant times tangent, must be secant of t. And I need a constant. And there's the final answer. The final answer is tangent of t plus secant of t plus your constant c. So again, always identify, is it an indefinite or is it a definite integral that we're trying to evaluate? Let's look at one last one. All right, so let's look at part E. I'm going to do part E right here, right below. So we're going to do the integral from 0 to pi thirds. Numerator is going to be sine of theta plus sine of theta times tangent squared of theta. Denominator is going to be secant squared theta, and this is all d theta. So again, the integrand is not in any form that we've seen so far, so we have to use some algebraic or trigonometric techniques. The technique that I probably want to use here is, since we have a monomial in the denominator, I want to split my fraction into those pieces, where we have sine of theta divided by secant squared of theta plus sine of theta times tangent squared of theta, all divided by secant squared of theta d theta. Well, let's see what the first part gets us. Sine of theta over secant of theta. Secant theta squared, that's 1 over cosine squared theta. Okay, so I'm just going to make a note of that here to see what we get. And actually, I am realizing I don't like this idea. So that's actually a bad idea, and bad idea on my part. So one of the things that I was looking at is maybe doing this as 1 over cosine squared, but if we do as 1 over cosine squared, then we're going to get cosine squared times sine of theta, which makes it harder to evaluate, because there is no antiderivative that we have seen so far that gets us sine of theta times cosine squared of theta. That's where my initial idea came from, that I don't want to go through with this. Instead, I'm going to go through the different routes. And again, sometimes you go one route and you see that that route doesn't take you where you want to go. So don't be discouraged. It happens. One thing that I did see as I looked up again is I saw that my numerator contains a sine of theta. So I'm going to factor out that sine of theta. And what I'm left with here is sine of theta multiplied by the quantity of 1 plus tangent squared of theta, all divided by secant squared of theta. And the reason why I decided to go back and try this approach here is because my numerator now contains 1 plus tangent squared of theta. 1 plus tangent squared of theta is a Pythagorean identity. That Pythagorean identity for 1 plus tangent squared theta is secant squared theta. And so when I initially saw that, or after I initially saw it, my mind said, hey, some stuff can then simplify. So 1 plus tangent theta becomes secant squared theta. Denominator is a secant squared theta. This is all still d theta, which means all we have to do is integrate from 0 to pi thirds sine of theta d theta. Now that is awesome. That we can definitely do. So as we then go through this integration, we're then going to say, okay, well, the integral for sine, we needed the antiderivative for sine, which will be cosine, but if we took the derivative for cosine, we would be looking at negative sign, but we don't have a negative sign. So the initial derivative that we took must have been negative cosine. So this will then be evaluating negative cosine of theta from 0 to pi thirds. So negative cosine at pi thirds, minus and minus, that's going to be a plus. Cosine of theta, which is cosine at 0. There we are. Cosine at pi thirds is 1/2. So that's going to be negative, so that's negative 1/2 plus 1, which means we get 1/2. There we are. So again, sometimes we go through, and again, like I said, you get a bad result, meaning something harder to integrate. That's okay. It happens. The thing about math is you have to try different approaches in order to get the approach that works best for you, or to get the approach that you can work with. So again, we want to keep working with this whole idea of identifying what is an indefinite, what is a definite integral, and how can we work on it. All right, so let's move on and let's talk about this whole idea of displacement and how we can calculate a total area for these types of integrals. All right, so let's talk about displacement versus total area. Here I have the integral. It says the integral from -1 to 3 for the bounds for the function x squared minus x minus 2 dx, where we have velocity that's given by the function x squared. Oops, excuse me here. Where we have velocity, I'm going to call this v of x. So I'm going to call my velocity here v of x. And it's given by the function x squared minus x minus 2. And this is going to be given in meters per second. So as we're measuring this velocity, it's going to be in meters per second. If we were measuring this in terms of the US customary system, then it would be in feet per second. Now, if I want to evaluate the integral as is, then that integral would give me a displacement, meaning that it would just measure the amount that I traveled from point A to point B. It wouldn't measure the total amount traveled. It'd just say, hey, you went from point A to point B, and the shortest line, that's going to be the displacement. Now, that area or that unit of measurement is going to be in meters, strictly just meters. Now, if we go about it in talking about the absolute value of the function, then we get to know what is that total distance that was then traveled. So the area still is in terms of meters. So in terms of meters, notice both of these areas on the picture on the right, both of those areas are above the x-axis, which means they're both going to produce a positive result. The picture on the left has more area below the x-axis, meaning if we just calculate the integral directly, it's going to calculate this integral to be a negative value, which again translates into that displacement versus the total distance. And that's what we want to get into. Is we want to start then observing what it means to be a displacement versus a total area or total distance covered. And what we're going to do is we want to find where this function intersects the x-axis. In other words, the x-intercepts. That way we can set the integrals and we can evaluate the integrals independently when we're talking about the absolute value of a function. So let's get into that with an example. All right, so here's the question that we're going to be working with. This says that the velocity function in meters per second is given for a particle moving along a line. So again, this particle is just moving along a line, and we're able to track its velocity. Its velocity function is given by v of t, which is given as t squared minus 2t minus 3, for the time interval between 2 and 4. We want to find two different parts here. Part A, we want to find the displacement, And part B, we want to find the distance traveled by the particle during the given time interval. So for part A, to answer the question for part A, if we want to find displacement, that means we just need to integrate the velocity function for the given time interval between 2 and 4. So integrating the velocity function from 2 to 4, we get t squared minus 2t minus 3. We're going to integrate this function with respect to dt. Add 1 to the exponent, so that's going to be t cubed multiplied by its reciprocal, minus, add 1 to the exponent, t squared multiplied by the reciprocal. Negative 2 is going to be multiplied by 1/2, so we're going to get negative 1, so it's just minus t squared, minus 3t, all of this evaluated from 2 to 4. So taking the function, evaluating it at 4, we get 1/3 multiplied by 4 cubed minus 4 squared minus 3 times 4. Subtract out 1/3 times 2 cubed minus 2 squared minus 3 times 2. There we are. So 4 cubed, we're going to go through that calculation really quick. 4 squared is 16, so, 4 squared is 16, so 16 times 4 should get us 64. So here we get 64 over 3 minus 16 minus 12 minus 2 cubed, that's 8, so that's going to be 8/3. Negative and negative, that's going to be a plus. 2 squared, that's 4. And negative, once again, that's going to be positive 6. Okay, we're going to go through and we're going to evaluate some of these fractions. 64 over 3 minus 8 over 3, that means we just subtract 64 minus 8. 64 minus 8 should give us 56. So we get 56 over 3. Then 16 minus 12, that should get us negative 28. Negative 28 plus 10, that should get us negative 18. So we have now 56 divided by 3 minus 18. So 56 divided by 3 minus 18, let's see if we can get this down. 3 times 18 should get us 54, so this will be 56 divided by 3 minus 54 divided by 3, and this should get us 2/3. So the displacement is 2/3 of a meter. Okay, so again, if you want to approximate this, that's okay, but I encourage you all to give me exact answers. The exact answer here would be 2/3. Now, we want to investigate this again using a total distance traveled. So again, the displacement just says, hey, this particle just traveled 2/3 of a meter. Let's see what the actual total distance traveled is. So in order to do this, I'm going to go with part B here. And for part B, total distance traveled, I need to integrate from 2 to 4, and this is going to be for the absolute value of the velocity function. So from 2 to 4, integral from 2 to 4, for the absolute value of x squared, sorry, I keep using x, it's t, t squared minus 2t minus 3, which means we need to find where this function crosses the x-axis. Where we find that the function crosses the x-axis, we'll then know where this function dips below the x-axis. That way we could then integrate the opposite of that function. In other words, attach a positive value to that. So we're going to find where v of t is equal to 0. So that's our first task. So I'm going to set t squared minus 2t minus 3 equal to 0. And I do believe this factors, let's see, is equal to 0. One of these has to be a positive. One of them has to be a negative. Larger number is going to be negative. T squared, negative 3, good so far. Negative 3t, 1t, that gets us 2t, which means t is equal to 3, or t is equal to negative 1. Awesome. All we need to know now is on the given interval from 2 to 4, we now need to find out where this now dips below the x-axis. All right, or below the t-axis. So I'm going to grab my line here, and I'm going to see where my function is negative. Okay, I have t is equal to negative 1. Now, t is equal to negative 1 over here, and then t is equal to 3 somewhere here. Notice the interval that we're working with is from 2 to 4. So I'm going to have the interval from 2 to 4, which means negative 1, we really don't need to really much care about negative 1. We just kind of need to know what's going on in between negative 1 and 3, because that's going to tell us what's going on between 2 and 3. So let's go ahead and let's pick a value in between negative 1 and 3. I like 0, so let's go with 0. If we choose 0 here, and let me put this in orange here. So if we choose 0, 0 is still in the interval from negative 1 to 3, which means it's still going to let me know what's going on between 2 and 3. Plug 0 into your function t squared minus 2t minus 3. When we plug in 0, we get negative, which means this area is sitting below the x-axis, or below the t-axis. So we have this area sitting below that x-axis. So that we know we're going to have to counteract in order to make that a positive area. Let's check the area from 3 to 4. Pick a number between 3 and 4. You could say 3.5. All right, so say that you choose 3.5. There we are. So if we choose 3.5, we're going to do 3.5 squared minus 2 times 3.5 minus 3, and we're going to get 9/4. All right, so we get here 9/4, and 9/4 is positive. So this area from 3 to 4 is sitting above that x-axis or that t-axis. So that's awesome to see. All right, now what we're going to go through is we're going to set up this integral then. So we're going to set up the integral from 2 to 3. So the integral from 2 to 3 is going to be evaluating this function, but remember that function is sitting below the x-axis, meaning that the area is going to produce a negative value. If we want to counteract it so that we get a positive value, then we need to multiply that function by a negative. It's going to be negative quantity of t squared minus 2t minus 3 dt, and then we're going to add this to the area from 3 to 4. That function is already producing a positive value, meaning it's already above the x-axis or the t-axis here, so we don't need to counteract that with any negatives. Everything's looking pretty good. All we need to do now is find that integral. So we're going to find these integrals then. All right, I'm going to move this down here. That way we can have a whole lot more space. Okay, so far we have this integral from 2 to 4, absolute value of velocity dt, and now we found where the area dipped below the t-axis, therefore we're going to counteract it. Now we're going to go through the process. All right, so I'm now going to start integrating this. The integral from 2 to 3, this is going to be for negative t squared. This is going to be negative 1/3 t cubed. Negative distributes. Negative times a negative is positive, 2t. So that's going to be plus t squared. Negative times a negative, that's going to be positive 3t. This is all evaluated from 2 to 3. Plus t squared, integrate that. That will get us 1/3 t cubed. Negative t, evaluate that. That's going to be negative t squared minus 3t. This one's evaluated from 3 to 4. So we have this first integral here. This one is going to be evaluated here. Then we have the second integral here. That one is going to be evaluated here. So let's finish this off. Negative 1/3 t, which is 3, cubed, plus 3 squared, plus 3 times 3, minus the function evaluated at 2. That's negative 1/3, 2 cubed, plus 2 squared, plus 3 times 2. So again, that was that first function. Great. Plus the second function evaluated at 4. So here we get 1/3 multiplied by 4 cubed minus 4 squared minus 3 times 4 minus 1/3 multiplied by 3 cubed minus 3 squared minus 3 times 3. And again, this one was that second function. There we are. So let's go through and let's simplify this as much as we can. Again, try to do all this without the calculator until it is absolutely necessary to use a calculator. So negative 1/3 minus 3 cubed. So same exponents, or sorry, same base. That means one of the exponents will cancel, and we're going to be left with 3 squared, which is 9. Negative 9 plus 9 plus 9. Negative times a negative, that's going to be a positive. 2 cubed, that's 8. 8 over 3. Again, distribute the negative. 2 squared, so it's going to be negative 4. Distribute the negative, that's going to be minus 6. So that first part evaluates to this, plus 4 cubed, it's going to be 64. 64 divided by 3, so that's just 64 over 3, minus 16, minus 12, minus 3 cubed. Once again, 3 cubed divided by 3, that's going to be minus 9. Distribute the negative. Negative times a negative, that's positive. 3 squared, that's 9. Negative times a negative, that's going to be another positive. 3 times 3, that's 9. That's the second piece. Now let's see what stuff will simplify here. Negative 9, they cancel. Negative 9, they cancel. I don't see anything else that cancels either, so I'm going to go through and I'm going to start adding my fractions. I have a 64 and I have an 8, so I'm going to do 8 plus 64. 8 plus 64 should get us 72. 72 is going to be divisible by 3, so we'll be able to reduce that in a bit. So 8 and 3, that's good. We also have 9 and 9, that's going to be 18. So I'm going to have an 18, and then I'll take this step by step. 18 minus 4 gets us 14. 14 minus 6 gets us 8. 8 minus 16 gets us negative 8. Negative 8 minus 12 gets us negative 20. So here we have minus 20. Now 72 divided by 3, that gets us 24, which means we have 24 minus 20, which is just 4. Which means the distance traveled is 4 meters. So 4 meters versus the displacement, which was given by 2/3, that's a big discrepancy. So we must always be on the lookout for those types of problems where we have to see what is the displacement versus what is the total distance traveled. Now we're going to talk about one more item, and this is going to be with regards to even and odd functions. All right, what it means to be an integral of an odd function, an integral of an even function. More importantly, what are the bounds that we're observing? All right, so I'm going to give you a quick depiction of this. That way we can then talk about it. All right, so here we're going to be talking about even and odd functions. So on the screen here, you have on the left side that if f of x is an even function on the interval from negative a to a, then the integral from negative a to a for the function f of x is equal to 2 times the integral from 0 to a for f of x dx. This means that we're going to be using symmetry. Because we know an even function is going to be symmetric along the y-axis, then if we're trying to find the area underneath the curve for an even function, where we have the left bound being the negative version of the right bound, then by symmetry, we're going to have double the amount of area as if we were just to integrate from 0 to that value of a. So here we know that we know that cosine is an even function. So that's what I'm working with here is cosine of x. So naturally, if I were to try to evaluate this, I would say the integral from negative pi halves to pi halves for cosine of x dx, well, cosine is an even function, identifying the bounds from negative pi halves to pi halves. That's the same bound except they're opposites, which means that I can just multiply double that area and just evaluate one side of it, meaning from 0 to pi halves for cosine of x dx. This in itself, evaluating one endpoint at 0, is always beneficial. Always going to be beneficial because, again, you don't have to go through the whole process of trying to identify what is pi or pi halves or 3 pi, so on and so forth. So that's awesome to see. Now, on the right-hand side, we see that if f of x is an odd function on the interval from negative a to a, then the integral from negative a to a for that function f of x is equal to 0. Now, this one's a little bit more interesting. If we're going to go from negative a to a, let's say we were going from for this function, we know that sine is an odd function, so let's say that we were going from negative pi to pi. All right, so if we went from negative pi to pi, here we see on the left-hand side of the y-axis, the area is below that x-axis. On the right-hand side of the y-axis, the area is above. Now, by symmetry, we should know that the areas are going to be equal. But the integral is calculating a net area, meaning that it's going to calculate the area below as negative and it's going to calculate the area above as positive. And if they're the same area, naturally they're going to cancel out. Which means if I have the integral from negative pi to pi for this function, which is sine of x dx, just by identifying sine as an odd function and it's going from negative pi to its opposite bound pi, I know that this will then evaluate to be 0. And again, we want to use these symmetric properties for functions. It's not just for sine and cosine, but it's more general in the sense of saying when you have an even function and when you have an odd function. Always pay attention to the bounds and always try to extract the bounds with the even and odd functions. If it works out, awesome. If it doesn't, it's okay. We can just keep going. So that's going to be it for this lesson. So please stick around and we'll talk about the substitution rule for integration and we'll carry on from there. Till then, have a great day.